Hey everybody, Chris McClure. We are now going to embark on covering a few sections from Chapter 6 as we wind up the summer semester. The big thing that we want to do here in Chapter 6 is at least get a fundamental, basic understanding of exponential and logarithm functions. Now, in order for us to understand those two functions and their relationship between each other, we need to talk about functions inverses with each other, which means that when you take a function composed with its inverse, that you'll get the identity function. So we're going to see exactly what that means, and we are going to begin the discussion by talking about what composite functions are. Here in section 6.1, this is going to be a short and easy section because doing compositions is pretty straightforward. You're basically taking functions of functions. So here's kind of a motivator right here. Let you read it. But basically what we're talking about here is imagine that you've got this ship with an oil slick coming out of it. Maybe it's got a leak. And this oil slick is roughly circular, like you see here. And suppose that this oil slick's circular pattern is increasing. It is increasing its radius at a rate of 3 feet per minute. So you can say that the radius is a function of time with the equation R of t is equal to 3t, where t is minutes since the leak started. And then what we would like to do is calculate the area. Well, what is the area of this leak? Well, what does it really depend? It depends on the radius, but the radius itself depends on time. So what you can do is you can compose the area function with the radius function so that you'll have area as a function of the radius, which itself is a function of time. So where you see the r within the area function, you can replace r by 3t. So now that area is going to be a function of time. So you're going to plug in 3t for r. So you have pi times 3t squared. And 3t squared is going to be 3 squared times t squared, which is 9 times t. So you have 9 pi times t squared, which is the area of that oil slick as a function of time. So what we just got done doing is we took the function of a function. In other words, we did a composite. We formed a composite function. And here's kind of what the notation looks like. Suppose that we've got two functions, f and g, and we're going to compose f with g to form this new composite function. Here's what the notation looks like. F circle g. And this reads f composed with g to form a new function. And so we're saying that f composed with g of x is really going to be f of g of x. So how you do this is going to be where you see where the independent variable is for f, you replace that independent variable x with whatever g of x is as a function to get a new function of x. Got to be careful though in terms of the domain. So the domain of the composite function really is going to be determined by looking at first at what is the domain of g, and then what is the domain of f in relation to g. So we'll take a look at what's going on here. When we form a composite function of f composed with g that we're seeing here, take a look at what's going on here. We have the domain of g. Remember, the domain is the set of inputs. So each value of x here is going to get assigned to some number, whatever g of x is, in the range of g. Now, maybe the result of doing that function g of x will result in a number that does not lie in the domain of f. But it could be that it does. like you see illustrated here, in which case then you can then map whatever g of x is into whatever f of g of x is in the range of f. Okay? Another way of visualizing the composition is by taking a look at the factories G and the factory F. So imagine, for example, in the automobile industry, that there are lots of manufacturers of car parts. For example, you might have a factory that manufactures engines. So input comes, some material, and out comes an engine. But this engine is then going to get shipped to the factory for the cars themselves, and then out comes a car. So the output of G is going to be the input of F. Okay? So let's see how this goes algebraically. Suppose that we've got function f here. F of x is equal to 2x squared plus 3. And we've got another function, g of x is equal to 4x cubed plus 1. And we're going to take a look at these various compositions. We're going to do f composed with g, and we're going to evaluate that at 1. We're also going to take g composed with f, evaluate it at 1. And by the way, f composed with g is not the same as g composed of f. And then we'll take a look at f composed with itself, evaluated at -2, and we'll also take a look at g composed with itself, evaluated at x equals -1. So let's start off with the first one, f composed with g. Now f composed with g of 1 is really the same thing as f of g of 1. Now, so what we need to do is find g of 1. That means for the g function, replace x by 1. So you have 4 times 1 cubed, which is 4, plus 1 is 5. So g of 1 is 5, so now we're looking at doing f of 5. And what's f of 5? F of 5 is 2 times 5 squared plus 3. But 5 squared is 25, times 2 is 50, plus 3 is 53. So f composed with g of 1 is equal to 53. And this is exactly how you carry out that composition and evaluate at a particular point. The output of g is the input of f. Let's go ahead and find g of f of 1. Now g of f of 1, well, f of 1 is 2 times 1 plus 3, which is 5. So now we're looking at g of 5. And when you replace x by 5 in the function, you got 4 times 5 cubed plus 1. Now 5 cubed is what? Is 125 times 4 is 500. Plus 1 is 501. So this right here demonstrates that f of g of 1 is not the same as g of f of 1 for most functions. Now, as you're going to see here in a minute, when f of g have a certain relationship, if that's the case, if f and g have some specific relationship called inverses of each other, then f of g is the same as g of f. But generally speaking, if you take any randomly selected function f and composed it with some other randomly selected function g, that f of g is not the same thing as g of f. All right, let's go ahead and evaluate f composed with itself of -2. Now, the output of f is going to be the input of f. Well, now f of -2, replace x by -2, you get 2 times -2 squared plus 3. Now -2 squared is 4, 2 times 4 is 8, plus 3 is 11. So f of -2 is the same thing as f of 11. And you have 2 times 11 squared plus 3. Now 11 squared is 121, times 2 is what? 242, plus 3 is 245. So f of -2 is 245. Now let's move on to the next composition, g composed with itself of -1. So here we go. That's the same thing as saying g of -1. Now g of -1 is going to be what? Negative 4 plus 1 is negative 3. And now what's g of negative 3? Now that's 4 times negative 3 squared plus 1. Now negative 3 squared is negative 27 times 4 plus 1. And that works out to be negative 107. Now let's see how we could use our graphing calculator to do that. Now let's just go into our graphing calculator. I want you to do this right now on your own. And I'm going to show you how to do it myself, of how to do these compositions. So I'm going to jump out of this real quick, and I'm going to go into my graphing calculator, and for y sub 1 in my equation editor, let me clear out that function there. I'm going to put in 2 times x squared plus 3. Enter. Now what was that other function? That other function was 4x cubed plus 1. So that's what I'm going to put in for y sub 2. 4 times, and in parentheses I'm going to put in my x cubed. Okay, well, if you have a graphing calculator that's like that, has that that automatic superscripting and the cursor stays up there, just hit the right arrow. That'll get the cursor out of that superscript. And then you can do your close parentheses. And let's see, that was plus 1. So we'll do the plus 1 here. Okay, so here on our graphing calculator, y sub 1 is the 2 times x squared plus 3. And the y sub 2 is the 4 times x cubed plus 1. Now, let's go ahead and quit out of that. And let's see how to do compositions. If you wanted to do f of g of x, that'd be the same thing as doing y sub 1 of y sub 2 of x. Now, let's evaluate that at specific numbers. Like, for example, you want to do f of g of 1. Well, then on the graphing calculator, we can just go into your variables menu, right arrow over to the y variables submenu, select option 1 for a function, and select that first option for y sub 1 there. So, and then in parentheses, because your graphing calculator does understand functional notation, so we're going to now do y sub 1 of y sub 2. So go back in your variables menu, y variables, function, and then y sub 2. Close parentheses. Now we're going to evaluate this at what number? Of 1. X equals 1. So plug in 1 in parentheses, close parentheses, and let's see what happens when we press enter. That didn't work out. Actually, I know what I need to do. Let's try this again. Go back. I didn't do that right. I need to left arrow, and let's delete this guy right here. And then right arrow and put a closing parentheses there. And that gave us 53, which is exactly what we have here. So this right here shows us how to do your f of g of 1. Or if you wanted to do g of f of 1, so on our graphing calculator, that means y sub 2 y sub 2 of y sub 1 and then enter, and that gets us 501, which is the same thing here. Or you can even compose a function with itself. Suppose that you want to do f composed with f of -2. So in our graphing calculator, that would be y sub 1 of y sub 1 of -2. So let's try that. Variables, variables, function, y sub 1 of y sub 1 and of -2, close parentheses, close parentheses. And that gave us what, 245, which is same thing. And your g of -1 on your graphing calculator, that would have been your y sub 2 of y sub 2 of -1, which is -107. Okay, so that's how you can use your graphing calculator to evaluate composite functions. Now let's talk about finding domains of composite functions, just like we want to be able to find the domain of any function. When we analyze functions, that's one of the first things that we ask. What is the set of allowable inputs? Now, it really comes down to, if we're taking composite of f with g, we need to first take a look at the domain of g, the innermost function. Now, the domain has no restrictions, so all real numbers will be the domain of g. Now, when you look at f, there aren't any restrictions on f either. So all outputs of g will be gladly accepted as inputs for f. So the domain of f of g of x will be all real numbers. Okay? And as a matter of fact, if you were to go ahead and take the composition of f with g, you replace, with an f, you replace x by the 4x plus 1 like we're doing here. And then you multiply it out, simplify, collect like terms. And 32x squared plus 12x plus 5, it really is the result of doing that composition. Okay, and indeed this function has no restrictions. So all real numbers will be in the domain for f of g. Now let's go in the other direction, g of f. And the story is that the innermost function f has no restrictions and g has no restrictions. So so if you go ahead and evaluate g of f, and remember this is f and that's going to be the input of g, so wherever you see x in the g function, you replace x by the 2x squared minus x plus 4, just like you see here. Multiply out and simplify, collect like terms, and again you see that this being a polynomial, there's no restrictions on x. So the domain for this composition is also the set of real numbers. A couple of things to note here, that if you're taking f composed with g, g is the innermost function, the output of g is the input of f, g of x must be defined in a way so x is not in the domain of g, or x not in the domain of g must be excluded. And then the composition f with g must be defined in such a way that the output of g must not be in the set of values of the independent variable of f that are excluded from the domain. Okay, so let's take a look at how that goes. Sounds a little confusing, but let's illustrate that. Suppose that we've got f of x is equal to 3 over x minus 5, and we've got g of x is equal to 2 over x plus 1. And we want to form the composition f composed with g of x. Now, g is the innermost function, so let's go ahead and see whether or not there are any restrictions on the domain of G. And indeed, you cannot divide by 0, so when you set the denominator of this rational function equal to 0 and solve for x, you see that when x is equal to -1, g of x is undefined. So we will exclude -1 from the domain of G. Now, in f of G, the output of G is going to be the input of f. And where you see x right here in this f function, x cannot be equal to 5, because if it is, the function is undefined. So what we would do now is to take the G function, and 2 times x plus 1 is the output of this function for input x. So what you do is replace x by 2 over x plus 1 in the f function, and set that whole denominator 2 over x plus 1 minus 5 equal to 0. Meaning we want to find the values of x such that 2 over x plus 1 is going to be equal to 5, and then exclude those values of x, because otherwise you'd be dividing by 0. So you want to find x such that g of x is not equal to 5. So that's what we're doing. We're going to set 2 over x plus 1 equal to 5, solve for x, maybe by multiplying both sides by x plus 1, multiply out. 5 times x plus 1 is 5x plus 5, subtract 5 from both sides, then divide by 5, and you get x equals -3/5. So you cannot let x be equal to -3/5, because if you do, then your composition is going to be undefined. Now, right here is the domain of the composition. Notice that you've got 2 numbers excluded from the set of real numbers. All other real numbers are the same, or are allowed. But if you were to form the composition f with g for those 2 functions, replace x by the 2 over x plus 1 within the f function, like you see here, and then you go through and simplify it, maybe by multiplying the numerator and denominator of the big fraction by the x plus 1, and then you go through and simplify, and you get this function here. Now, for this function right here, you see that when x is equal to a -3/5, this function right here would be undefined. So what's the problem with, let me go back, what's the problem with x -1? Now, here's the thing. If all you were looking at was this function right here, then yeah, just excluding -3/5 would be enough to, to show the domain for this function right here. But that would not be reflecting the fact that we got this function by doing the composition of these 2 functions here. So when we explicitly say that we compose these 2 functions, and then what is the domain of that, then you have to individually look at the restrictions on the domain for g of x, and then for the outer function f, by setting g of x equal to whatever you need to in order to make the denominator equal to 0 for f. Okay, so that's why we have this for the domain of our composition compared to the domain for this rational function itself, not knowing that's the result of the composition, which we would only exclude the -3/5. All right, now let's go ahead and take f with itself, the composition of f with itself. What would be the domain of f composed with itself? Well, we can go through the same process. First of all, the innermost function is f, and of course we would have to exclude 5. Okay, and then take also a look at, for what values of x will 3 over x minus 5 equal to 0, like you see here. So, and that would be, 28/5. If you were to set the 3 over x minus 5 equal to 0 and solve for x, you get 28/5. Or you can just do what they do, is after you had already excluded whatever you needed to from the innermost function, then just go ahead and carry out that composition and then find out what restrictions that you need for the final function, which in this case would be the same, 28/5. Okay, let's do yet another example, but this time we're going to show that for some functions, some pairs of functions, that when you do f composed with g, that it turns out that's the same thing as g composed with f. And let me just reiterate, this is not generally the case for all pairs of functions, but there are some pairs of functions whose compositions with each other are the same in both directions. So let's go ahead and show that f composed with g of x is the same as g composed of f. Now, when you take f composed with g, well, here's g, and that's going to be the input for f. So in the f function, you just replaced x by whatever g is, and then multiply out and simplify. And that actually works out to be x. And then we go through and do the same sort of calculation in the other direction. Let's take g composed with f. Replace x by f of x within the g function. And that works out to also be x. So interestingly enough, f of g of x is equal to x, and g of f of x is equal to x as well. So what does that mean? Well, as it turns out, it just means that f and g are inverse functions of each other. But shh, I didn't tell you that until next time. Yes, on your graphing calculator, you can go ahead and take the pair of functions composed with each other and verify indeed that they would give you when you graph those compositions, that you'd get the graph y equals x. I'll let you do that yourself. Now, if you have a complicated function, you could write the function as a composite function. And for those of you going on calculus, this is going to be an important skill. So suppose that you have, for example, the function x squared plus 1 raised to the 50th power. How can you write that as a composite function? Well, there's some various options. But one option that you have is you can have x squared plus 1 as your inner function, like g. So you can let g be equal to x squared plus 1. And then you can let your outer function f be equal to the x to the 50th power, this power function. So do you see how f of g of x would be equal to the x squared plus 1 raised to the 50th power? Just like we see here. So you can kind of decompose a lot of functions out there as composite functions. In fact, you can even write g of x as a composite function. Maybe composed between the x squared function and the x plus 1 function. So you could even do a composition with 3 functions if you really wanted to. Okay. How about this function right here? Can you write this function, 3 over x minus 5 squared, as a composite function? Well, how about trying this? Suppose that you let your g of x be equal to the x minus 5 function. That would be the inner function. And then your 3 over x squared function, let that be the outer function, your f function. So that when you do your f of g of x, you get 3 over x minus 5 squared. So yeah, we did another composite decomposition. Okay, so that's it for composite functions. And when we come back, we are going to take a look at what it means for two functions to be inverse functions, so we can formally introduce that idea. Okay, so that's it for today, and I'll see you tomorrow.